Hello, my name is Andres Quast, and this is my Physics 2211 Lab 5. Little introduction here. So, in this lab, we're going to be observing the motion of a falling spring and comparing that to its computational model. I will show the slinky first compresses before the bottom of the spring compresses, will first compress, and then we'll begin falling to the ground. So in order to observe this and model this, I'll be using a tracker software to analyze the location of the top of the spring, then extract the data from this tracker, and then write code to model the spring situation and gather the data it provides. With this, I will create energy graphs to model what is happening with the slinky, and then I will compare the tracker data to the computational data. Here are some fundamental principles that I'll be using, which are Newton's second law and the velocity and position update formulas. So the tracker software that I am using allows me to take a video, such as the one you can see on your left, and turn it into data points as you can see on your right. Here's the video I used. We'll see in a second. The initial conditions are that the mass of the slinky is approximately 0.204 kg, and the drag constant I use is 0.102. And our system is a slinky in the earth, and there are surroundings like the air resistance and more, but the other ones I've left out just because they're not very applicable to the situation. So here's the video. Wow, that was pretty awesome. Nope. Okay, so here's my code, as you can see, that I will be using to model what happened there. We have the initial ball and its ball position and ball velocity, that's its initial velocity. And you can see the constants we use as gravity, J hat to show the direction that the ball is falling in, B, which is our drag force constant, and then spring constant, which is what we have there at K. And then we see that basically what I did is I broke it up into 2 times. When t, or the time, is less than 0.27 seconds, the ball will follow those different things, or sorry, not the ball, but the spring will. And the forces that are acting on the spring in that situation are weight force and tension force, which are the forces between the spring and the force between the spring and earth. That weight force, the tension force is basically what is compressing the spring together. And then we can see that in the second part, instead of having the weight force and the tension force, we have the weight force and the drag force, which is shown as below, and that's how we calculate Fnet. In both of these, we update the position and the velocity, and then print out the y positions. So here is the data graphed from both the observed model and the computational model. As you can see, they both follow a generally similar trajectory. So in conclusion, the computational model did reinforce the observational model's data. The difference in the models could be a product of mistakes when applying positions in the tracker. Additionally, because I was observing the video, the mass, drag, and more were not necessarily factual. Alright, thank you guys. Have a good one.